Hello. Hi guys, ki hai chal? I hope you guys are doing good. In this, we're gonna see complete crash course of a segment tree. Again, I'll walk you through the entire syllabus, but the code, the notes, all that you will get soon on codewitharyan.com. Although not right now, it is there, but soon, around in a month, you will have it after this video is posted. Now, the syllabus, we'll firstly cover what are segment trees. Next, we'll cover why actually we use segment trees. Instead, we have fenwick trees, we have prefix sums. We have already had one course or one part of fenwick trees. If you're not watching, just you can go and watch it. But still, if we have these, then why still we are using a segment tree? What's so special about segment tree? Then we will see actual implementation of segment tree while going through its basics. Then we'll go on to segment tree with lazy propagation again. Although many people are scared of segment trees and especially lazy propagation, but I swear it is easy as F. Now, easy as E, but I'll say F. Next, we'll see a generic segment tree template or a code, you can say, because if you have been following us, we have given a binary search template, we have given a 2-pointers template. In 99% problems that can be used. Same way in this, you can use that generic template. And again, with using that template itself, we will use 10 problems and same many more problems can be solved. Just a quick modification here and there and you're good to go. No changing code of the entire segment tree, not required. Lastly, I'll give you a quick hint about what is a descent segment tree or and also merge sort tree, right? And again, 40 plus practice problems you can find here, right? Again, the entire code approaches everything. Again, why I'm saying again, but yeah, entire code and everything. What are the notations used? All that is taken from CP algorithms so as to be consistent. If you want to practice more problems or if you want to study much more further, then you will go and refer the CP algorithms, right? And that it will help you what you will study right now. Now let's start off with our actual segment tree. Firstly, if you don't know, I'll tell you, segment tree is famous for its range queries. Again, if you will think of range queries, then you will think, Aryan, we have already seen that range queries can also be solved by using fenwick trees, and also we have seen other ranged based data structure. For example, if you don't know, there's RMQ, range union query, we have sparse tables, we have prefix sums, we have fenwick trees. If you're confused on what fenwick tree is, why I cannot use prefix sums for my range queries, then just go and watch this one video. Link will be in description. But if you know, okay, it can still be solved. The same thing can be solved by using my segment tree. Just remember, segment tree is BAP as in father of every range query available. Although it is a bit slower than other algorithms. Again, when I say bit slower, it actually incurs some login factors, building up, extra space is used, but it is actually the father. Now, segment tree, what is the advantage? Although we have studied other range data structures, but what is the advantage of segment tree? Firstly, it is super duper versatile. I repeat, I actually added a duper. I didn't even know the spelling of it, but still I added. It is super duper versatile. This, to know this fact, I will go on to it a little bit more further on, but still it is super duper versatile. Next is that fenwick tree. We always have the range starting from the beginning, which means the prefix. But again, if you don't know, in a fenwick tree, which is kind of a younger brother of my segment tree, as you can say, he has lesser responsibility, he has lesser functionality and stuff. That's what we see in fenwick tree, that okay, we are actually starting from the prefix itself, if you remember. But in this, we maintain for every possible ranges, the answer is there. And the biggest thing, if the solution is not invertible, which means if you know min max, we cannot use a fenwick tree. If you remembered, we did this problem, block placement queries. If you don't know what the problem is, check the description or write the problem name by Aryan Mittal, you'll get the video. You will recognize how a fenwick tree is, it's so hard. Again, when I say invertible, which means, okay, if I ask you, if you have some range maximum query, if you update something and if you want, okay, my current value is 5, I want to update it with a 3, I cannot do it because I can only increase the value, I cannot decrease it if I have a maximum. Same way for minimum, I cannot go reverse. And we actually encountered this problem in our this block placement queries problem. Although we have to find some hacks around it, but finding hacks takes time, and also it is very much typical to actually understanding code. While in our case, I can say, okay, update anything, assign anything, do a range query of maximum, minimum, or anything. Nothing is correlated with each other, which means updating a value is not related to querying a value. We'll see everything, but I'm just showing you what are actually the benefits of segment tree. Again, segment tree is super flexible data structure. What I mean by that is that I can answer much more complex problems by simply using my segment tree, because everything is so visible and everything is so modifiable that, again, when I say everything, I mean the node structure. Again, I'll go on to it very deeply, that what I mean by node structure, how it is so modifiable, but I can answer super complex queries with also segment tree, which simply means that a single node can store many values. Again, you will be very confused. Okay, Aryan, what is node? No worries. I'm just telling you what are the benefits if someone asks you. Last but not least, one important property before we start on with the actual segment tree is that segment tree requires only a linear amount of memory. People just think, okay, Aryan, I'm building under a tree, I will be having many more things which I will store. No, bro. You know that a Fenwick tree and other range-based queries, they require linear amount of memory. Same way, my segment tree also requires a O of 4n memory. Again, you might be thinking, okay, why 4n, why other require O of n and stuff, but no worries, we'll go on to it also later on. Now, you know the benefits of segment tree. Let's start off with actual segment tree. As we have already had the spoiler that we can do range queries. The star mark is, although range queries can be done by many data structures, but with updates. Now, range query as in, I can find the range minimum, range maximum, range sum, range multiply, range GCD, range XOR, range, it goes on. But okay, Aryan, but where it will go on? Up till how far? What operation I can apply? No worries, I'll go on to later on. No worries. But the list keeps on, like list goes on and on. And again, with updates is a very specific fact why we will be needing our lazy propagation in future. But if you don't know why updates is why it's a super big thing, why I'm so hyped about it, please just go and watch this one video in which you will recognize that why prefix sums cannot be used, which is very commonly known range-based query structure, data structure. Now, you will see that we have these operations. I will have update and query. I can update any element or any range. I can query any element or any range. Now, update can be anything. Here in this case, let's say XOR. Query can be also anything. Let's say I take a sum, which means I'm updating by saying, bro, update and do a XOR while updating, but while querying, do a sum. Everything, every possible combination is possible. So you will be worried, okay, Aryan, but how big is this list? There is no list as such. The list just simply says any associative operation can be done by simply using our segment tree. What I mean by associative operation? Associative operation simply says that A plus B bracket plus C is equal to A plus bracket B plus C. Anything which follows associativity will also follow our segment tree rules. You can easily say that maximum of A comma B comma C, maximum of A comma max of B comma C. It also follows our associativity rule. So if in future, if you are worried to think, Aryan, you never told any problem involving GCD, can I apply GCD on segment tree? Yes, you can, because it is associative. Right? So any operation you encounter in the operation can also be made, because right now, okay, these are very common operations, but what if a code force problem simply says operation is a function, you have to apply a function, and that's an operation. How will you know if you can apply a segment tree or not? this function should be associative. Then you can apply it. Okay, now we know that what are operations I can apply on my segment tree. But for simplicity, until I reach on to the problem discussion, I will take simple range sum query. Again, for simplicity, I will generalize. I will take 10 problems also after that. But for simplicity, for entire explanation, from segment tree to lazy propagation to generic segment tree, I will take range sum query. And again, simply, I'll give you by examples also. With again, make sure with updates. Now let's start off by simply seeing that what a segment tree is. The word itself says segment tree. You have an input array. As you can see, this is my input array. See, input array is 1, 2, 1, 4, 2, 3, 1, 1. Input array, again, index is also 0, 1. You take segments or portions of this array and make a tree out of it. Remember, maksad nahi bholna hai. Your main aim was range sum query. So what I did was I took segments. Okay, I took this segment. I take the sum of that tree. And again, I want to make it as a node or a tree structure. So I made it 3. I take this segment 1, 4, and then I added, okay, it became 5. 2, 3 added, it became a 5. 1, 1 added, it became a 2. Same with 3, 5 added, it became a 8. 5, 2 added, it became a 7. 8 and 7 added, it became a 15. So this is what a segment tree is. Make segments and apply your query whatsoever you want, and that's how you build a tree. Before going on further, this lecture and entire crash course, it takes a lot of effort and time to make all these notes and stuff. So it will be very helpful if you can just like it and share with your friends. Please. Thank you. Now, so this is what a segment tree is. Now, what actually it is doing, you realized very easily. But how to build it? Okay, you realize what it is doing, but how to build it? It's a question, right? The question is simply, you can, maybe if you want, you can take pointers, you can make a tree. If you remember, if you have done 3 problems, you know, you have a left and right pointer, you store the entire pointer and structure. Storing a pointer, which means storing some space for that pointer, right? Which means you will store some space for that pointer also, which would have taken some extra space. Thus, we utilized our one basic funda that how we can design or basically put our tree inside the array itself. So I will show you. What I did was I made these tree nodes and I numbered them in the indexes of the array. I will convert this entire tree to just one single array, so as to not use any extra memory, because our main aim is to decrease time, decrease memory. I'll use as minimum memory as possible. So what I did was, okay, I had the node. I indexed it at 1. Why 1? You will see later on. But you will see how it will help me is, if I have the index 1, its left child will be current value. Again, let's say the index value is v. Its left child will be 2 into v. Its right child will be 2 into v plus 1. And the same will follow, and same will be followed by the entire tree. If it is 2, its left child will be 2 into 2. Its right child will be 2 into 2 plus 1. Again, it is 3. 3 into 2, 6. 3 into 2 plus 1, 7. And the same way, 4, it became a 8. 4, it became a 9. 5, it became a 10. 5, it became a 11. 6, it became a 12. 6, it became a 13. 7, it became a 14. 7, it became 15. So, if I want, I can represent this entire tree as an array itself, in which this at index 1, it says I am the root, and these, which means 2 into 1 and 2 into 1 plus 1 are my children. This 2 will say, okay, I am, let's say, another value. My children are 4 and 5. Thus, by simply using an array, I was able to represent my tree. Thus, using or basically efficiently utilizing my space. Now, we simply saw that, okay, our root will be at v, and we had 2 into v plus 1, and so 2 into v and 2 into v plus 1, which are the actual indexes of our tree. Now comes the fact that what is the space used. Although, if you had known that this is 1, this is 2, this is 4, this is 8. So at every level, I am actually increasing. At every level, I am actually doubling up my number of nodes. And this was my input node or input array, which is n, right? Imagine it has n nodes. So with a simple tree property, I can easily say that the entire remaining tree will have again n nodes. If I take the summation, it will be roughly close to n minus 1. So I can say it will have n nodes roughly. So in total, this would have ideally required a space of 2 into n. But if you remember in the very beginning, I told you the space used is actually O of 4n because we initialize this tree array. Remember, tree array by why tree array? Because it's a segment tree array. I initialize it with actually 4n. Why is that the case? That is the case because if we consider the best case scenario where every node is there, but I can show you a simple example of not the best case. What if you had one? Again, remember, like imagine that you have this nums or basically the input array as 1, 2, 1, 4, 2, 5 or 4, 3, 5. I have only 6 elements, right? So while when you start building the tree, you will see, okay, 1, 2, 3, 2, 4, 5 and 3, 6, 7. For 4, it will be 8, 9. For 5, it would have 10 and 11, but for sure, I have no nodes. For 6, it is 12 and 13. For 7, it is 14, 15. So you can easily see that these nodes are missing. These nodes are missing, basically not there. But still, I have to keep space in my array for them. But you will say, it's a waste of space. No, it is not. It is super optimal what we can do, considering we are not using pointers, which will take super extra space. So we realize it is not that enough to keep only 2n, so I will have to keep more. Thus, we keep a 4n as a memory space for us. Now, although a bit space is wasted because of empty cells, but that is okay for us. That will not give much effect to us. Now when we have known the entire rough structure of how a segment tree works or how a segment tree is, now let's move on to how we will code this thing up. Firstly, before coding up, you need to build up the segment tree. Although we build up logically, but how to build up in the code? We'll build up the segment tree by code. Now, as it's a tree, so I assume that you should be knowing a basic tree traversal, which is a simple DFS traversal. If you know a simple DFS, simple recursion, you should be good to proceed further. If not, just go and watch this one video to understand how a DFS works, how I use the property or the information of my children to use them, because I'm not good. I use my children. That's what a tree does. He uses his children to get the property for him, which is simply performed by using a DFS. Now, proceeding further, if you remembered a while back, we showed that I will start off from the index 1, which will act as a root. But if you know, in the very beginning, you have only the leaf nodes of the tree, which means you have the input array is the leaf nodes. So this value, although you will start off from the root, which is at index 1, but you will build these answers while coming back. Now we know we'll apply simple DFS, which is simple recursion. Simple recursion says that if you want to perform any operation while coming back, you perform this operation after the recursion or after the recursive step. So what I will do, I know I will firstly start off from index 1. I should be knowing the range of this, which is from 0, as you can see, my 0 to my length minus 1. Again, if the length is 8, so length minus 1 will be 7. So I know this is my range. I should simply keep traversing. As soon as I reach my end, as soon as I reach my leaf nodes, while coming up, I should build my answer. I should build my answer. I can say I should build my tree. Let's see the code. Again, I will use some basic symbols, or I should say notations. These symbols are specifically used by taking consideration they are in line with CP algorithms. This is the only website, or you can say the God website, for studying and again mostly studying and a bit practicing for CP problems. So no matter what, if you study from me, if in future you want to just have a quick recap while giving a contest, you cannot watch the entire crash course. You can watch though, but still, you can just refer the cpalgorithms.com and you can just get that idea. Now, T will define the segment tree array. You know, the tree which we built of 4n size, the entire tree which we represent as an array. That will be our T. V is the segment tree vertex, which I was talking about so far. V, 2 into V, and so on and so forth. So V is the segment tree vertex of this array T. Cool. TL and TR, it is the range of my segment tree, which is, as you can see, 0 and n-1, which is the range, input array range, I can say. Now, let's build up the segment tree. Again, in a simple recursion, we know this is build is a function which requires the input array, which is this input array, right? It requires my V. It is the index. Remember, it is the index. V is the index of our tree. I require a V. I require a TL left, which is 0, and TR, which is right. As you can see, I have also commented it. Every code, every links will be in the video itself. So no worries. I will give you everything. No worries. And again, you might think, Aryan, where is the T defined? Where is the T vector defined? No worries. Everything will be done. Go with me. Now, you have to build. For building, you need these stuff. Okay. Makes sense. So, for building, what you do? I know the array range, I have to reach to my leaf. At every point, if I have, I know in the very beginning, I have my ranges 0 to 7, both included. I will cut it in half. I will ask for 0 to 3. Then I will ask for my 4 to 7. Then again, this will cut it again in half and will ask for this range and this range. Again half, this range. See, every time it is doing half and asking for both the ranges. When it will stop? It will stop when the range length is itself 1. How will the range length be 1? Only when my TL is equal to TR. Because the range length is TR minus TL plus 1. So if both are equal, the range length will be 1. If the range length is 1, which means I have reached the leaf node. If I have reached the leaf node, just put that leaf node in my tree. So in my tree, again, V is the vertex, if you know, or you can say index. I will simply say, bro, put this specific, again, A is the input array, TL is the index. You know that I have been again, TL and TR both are equal. So you can put a TL or a TR, both will work. But this will work because I have reached my one single index. That is it. Okay. So leaf node is built up. You know that what you were doing? You were finding the mid, which is TM. TM is the mid index. By saying you have a TL left, TR right, you do a by 2 simply as we do in bind search. You find the mid. Using that mid, you will ask the recursion first, saying A input vector. You are going to a child. Left child will be 2 into V. Right child will be 2 into V plus 1. With for the left child, the range will be TL to TM. For the right child, the range will be TM plus 1 to TR. Right? So for the left child, range will be TL to TM. For the right child, range will be TM plus 1 to TR. Now, when I have done the recursion, while coming back, I should compute my answer. In this case, I told you, I'm taking a range sum. So, whatsoever I have got from the left child, whatsoever I've got from the right child, I should just sum that up. And I will take that summation from left and right and I'll get the 3. So, I'll take the summation from my left child for a V. Its left child will be 2 into V. Right child will be 2 into V plus 1. So, I'll take the summation of both of them. And that is how I will get my answer. And thus, I was by simply a simple recursive code, I was able to build my tree. Or I can say my segment tree. Now, the simple time, as you are doing a simple DFS traversal on the entire nodes of the tree, it's just O of n. Space you have already defined as T. T will be defined in the very beginning as 4n. Although, you know, I'll go into every operations, but I have not initialized tree here. So you might think, okay, where did T come from? No worries. But so far you have seen the tree is now built. Now, again, I just given a quick explanation that in the last when you're coming back, you would have got the answer of 2 into v, which is the left child, 2 into v plus 1, which is the right child. So you can simply use those to get your parent answer. When the tree building is done, you are good to start querying for any query, which our segment tree we will use for. So let's see that if you have built this tree, I ask you to query for this range from 1 to index 5, from index L to R. L is 1, R is 5. I'm asking you to query it. When I say query, I indirectly mean give me a range sum query. So I am trying to ask you what is the summation. Now to optimize this query, what our segment tree uses is, again, you know, I have in my mind, I have to go and search for this range 1 to 5. Anything outside this range, I'm not concerned about. Anything inside this range, I'm concerned about. So what this tree is storing, let's take a look again. If this node is storing the answer for the range 0 to 1, as you can see, this range. This 5 is showing the answer for this range. This is showing the answer for this range. This is showing the answer for this range. Same way, this it is showing the answer for this entire range. This is showing the answer for this entire range. Ultimately, this 15 is showing the answer for this entire range. That is how useful my query is. Why it is useful? It is useful. What if I would have asked you, Aryan, give me the answer for this entire range? Give me the answer, which means give me the range sum for the entire range. You don't need to go anywhere. Just simply ask the root. That's your answer. If I ask you, Aryan, give me the entire left range answer, go and ask its child. 8 is the answer. Right range answer, right child, 7 is the answer. But I took an example in which the query is somewhat in the middle, somewhat in the right, somewhat in the left. How will you get the answer for it? Simply, we will see where we want to go. Again, from the very beginning, our query, I will start by saying I will start from the root node. Root node as it is at index 1. Left child is at index 0. Right child, sorry, left limit is at index 0. Right limit is index 7. Now, for me, it is V1, TLTR is 0 to 7. For me, the query I was asking you was query from range 1 to 5, which is this range I was asking you to query. Firstly, if I look, I should ask myself, should I go left? Should I go right? Should I actually not even, I don't even need to go anywhere. I should return from here itself if I got the answer. How I will know it? I will know only when the required range, for me the required range is L, R. L, R. And for me, the current node V on which I am standing right now is showing the answer for 0, 7. 0, 7. So it is lying in the middle, which means, okay, as in it is lying in between. It is not completely in line. So I should go and ask my left and right. So this simply says it's a partial overlap. Whenever I have a partial overlap, I should go and query for left. I should go and query for right. Now, what I will do, I will go and query for left. Again, remember, as we go on to left, what will happen? What will happen to your TL and TR? Same way, as we are going on to the child, and that is a left child, that its new range will be TL to TM. Right child range will be TM plus 1, TM plus 1 to TR. Right. So I will simply get this up. So what I did, I got a TL as 0 and TM. Again, a new TR will be my TM. So that will be my 3, which is mid. So this is my new range. Again, the input range still remains intact, 1 to 5. I want to still get the answer for 1 to 5. It is again a partial overlap, because you can see it's a partially overlapping, not completely overlap. Still, I should go and try for left and right. I will go and try for left, I'll go and try for right. Let's see again. If you see, it will be a 0 and 3 current range. I want to query for 1 to 5. The left range is from 0 to 1. So I might have something, I might not have. But for simplicity, let's quickly jump on to right and see what's happening on right. Although it will jump on left also and right also. On right, when it will jump, it will query for L to R. That's a query which we wanted. The current range will be 2 to 3 because of T. Again, mid I will find, mid will be 3 by 2, so mid will be 1. So right range will be Tm plus 1, which is 1 plus 1, which is 2. So it will be 2 to 3 is the right range. 2 to 3 is the right range, and I can easily see that now it is a complete overlap. The input range on which I am at is completely lying under the query range, which is L to R. So I don't need to go any further. I should return from here whatsoever answer I have got. What's the answer I've got? I have got the answer as 5. So I've got the answer 5. It was a complete overlap. I should return 5 from here. How I know? How I got to know that? I got to know if I have a complete overlap. How to know that? By simply seeing. See this example. L is less than equal to my TL. R is more than equal to my TR. L is less than equal to my TL. R is more than equal to my TR. In that case, it's a complete overlap. In that case, return whatsoever answer you have stored at that tree node. For me, it was a 5. I returned it. What about the partial overlap? Again, in the partial overlap case, as in this case, I know in the partial overlap, I told you I will go and try for both left and right. So I will split in the middle, which means again Tm will be TL plus TR by 2, and then again go and query for left, which is 2 into V, go and query for right, which is 2 into V plus 1. Again, in the left, the range will be TL comma Tm, split it at the mid, and right range will be Tm plus 1 comma TR. Cool. And again, simply go on until you find a complete overlap. As you can see, in this case, it will again would have got a partial overlap because the range is 0, 1, the input range is 1, 5. It would have again went on to left and right, but right would have been successful. Thus, it would have returned a 2 from the right side, 5 from this node, and if I just go on, it will be 5 from this node also. So I will return. But Aryan, you discussed partial overlap, you discussed complete overlap. What about the no overlap? Okay, in no overlap case, as in this case, there was no overlap. The range was a 0, while I am at 1 to 5. As in this case also, the range is from 6 to 7, while I am at 1 to 5. In a no overlap case, return anything which will not impact your answer. So in no overlap case, where my TL is more, again, if let's imagine your L and R is here. So if your TL, the left of your, it is more than your R, or if your TR, if it is less than your L, in that case, return something that will not impact your answer. In this case, the something will be 0, because if, see, you are doing a range summation, A, you are adding a 0. This will never impact your answer. This is called as an identity element. Remember this, it will be used a lot when I will go on to generic code. So you are adding something which will not impact your answer. That adding something is called as an identity element. If the operation would have been multiplication, I should have written something which would not impact my answer. That something would have been a 1, because 1 is the identity element for multiplication. Now we realize these are the identity elements. They will depend upon the corresponding operation. Multiplication, I have 1, plus I have 0, or I have 0. Same, like it's a simple way saying apply some operation, after which element should remain as it is. That is called as an identity element. And again, the operation applied or the transformation used is called as an identity transformation. Now we have got how we will query our entire tree. It is entirely purely DFS, no segment tree. The people who are scared of segment trees by their name, else it is purely DFS. So you queried, you will simply pass in the initial V, which is 1, initial left range, which is 0, initial right range, which is length minus 1, actual input, which is L comma R. You might feel like, Aryan, it is redundant to pass this information. I will say you are correct. That is the reason in the code, when I will show you, I will override these methods. I will override these methods so that I don't need to pass these at all. It is actually redundant to pass them. It will always be starting from these values. So it's redundant. Now, but the input for me, which is required, is L comma R. Let's see how I will use it. I will simply use it by saying that, again, please don't bash me by saying, Aryan, what is V, what is TR, what is TR? The same has been used by your CP algorithms also. Now, same way, if it is no overlap, return a identity element. If it is complete overlap, return the value stored at that node of the tree. If it's a partial overlap, find the mid, go and query the left side, get the answer, go and query the right side, get the answer. When you have the answer while coming up, just apply your operation. You want the range sum, so you applied the summation operation on the left and the right ranges, and thus getting the answer. That's your range query done. Now comes on, what is the complexity of this range query? Because it might feel, okay, Aryan, you are going on to like nearly all the nodes. You went on here, you went on here, then you went on here, then you went on here also to check ideally. It's just that you did not go on to the leaf nodes. So are you saying for one query you will take O of n time? No. What's happening? Again, the reason I took that example just to show you the worst case possible. Now, what's happening? Firstly, I'll ask you a very quick question. What is the length of this, or basically the height of this tree? What's the height of this tree? Ask me, tell me. The height of this tree is simply log n to the base 2. How? At every step, I am increasing the number of nodes by 2. Here I have 1 node, 2 node, 4 node, 8 node. So imagine in total I have n nodes in the entire tree. Height will be log n to the base 2. Okay, height is sorted. Now check what I was doing. I will go on to either left or right. What I mean by that is, if I am here, I will either go on to left or right. But Aryan, you went on to both the sides. Yeah, correct. For the root node. For this node, I will either go to left or right. Aryan, you again went to both the sides. Yeah, exactly. I went to both the sides. But if I am going on to the left side, which means I will for sure completely take the right side. In this case, when I went on to right here, if I'm going on to right side, it means for sure I will completely take my left side, which means in the entire subtree of left, I don't need to go further. Thus, my claim was at any point of time, apart from the root node, I am going on to either left or right. In case I go on to both the sides, which means one side I will completely take, other side I might ignore. So you might think, Aryan, are you saying it true? Yeah, it is. In this case only, when you had this range, you went on to both the sides because it was also coming on the right side. Then when I asked you, should you go on to right or left? You, let's say, said, I want to go to both the sides, right and left also. Thus, my claim was, if you're going on to both left and right, it is for sure you will take it completely, considering you also went on to right here. There are many considering. See, the only thing which you have to see is, if you go on to right here, which means for sure you are also again, I am trying to see the worst case possible. Worst case is as many left and right. That's a worst case, right? So if it has gone to right, which means he is saying in the middle half, I have something. So if I went on to left, and again I'm also saying I should go on to left also. So I'm saying, okay, in this middle half, I have something in the left. He's saying he has something in the right, which means this portion should also be included because it's a range query. If I have something in the left, I have something in the right, for sure that should be connected, and thus this entire portion will be included. For to showcase the example, imagine you had this range. You know you have to go on to both the sides. Okay, you went to both the sides, no worries. But at this point, if you have to go on the left side, which means the entire right range will be included. In this point, if you have to go on the right side, the entire left range, this one would have been included. But in this case, you will see, I did not go to my left, thus I will go on to my, I did not go to my right, thus I will go on to my left. Now again, for left, I again can have many options. I can go on to left also, right also. But you will see that how I'm restricting either left or a right. So at any point of time, I will have only two options. And thus, I'm not saying two options at every point. Nah, every point in every level, I have just two options. At max, two options. And I know I have log n levels. Thus, the complexity of query will be O of 2 into log n, or you can say easily as log n. Now, same way for this example, you went on to left. You did not even go to right. Thus, at this point, you again have two options. You can go to left also, and again, you can go to right also. I'm not saying you will completely take it as it is. No. Firstly, you will go on to left, and then you figure out, okay, it is complete. Then you can take it. It was different than that of saying blindly, as I remembered, I took a left here, so I took a right here, so I should blindly take this because it will for sure be included. In this case, you will see again, there are one option, two option, that's it. Here I have one option, two option, that's it. That's how I'm saying. Again, for this example, at this point, I'm not even going here. Again, two options at max. At this point, if I'm going to the left, sorry, I'm going to the right, which means this will not be included. Okay, not included. And again, at this point, I'm going to the left. I'm just getting this point. Thus, I will have the complexity as O of log n. Now, coming on to update. Here we will update single element of my array. Imagine I have this input array, which was the same so far. You updated this element at index 2 of the input array. You updated it and said, bro, it was no matter what earlier, I will update it to a value 10. So I am telling you the point update. A single index or a single point should be updated. So what we will do? Simply, we will go and find that specific index 2. We will reach that index 2 and then we'll update it and then build my tree again. So how I will reach there? I know the index is 2. I am currently at a 0,7, right? If you remembered, this is storing 0,7. You just have to locate. Where will you find a index 2? Simply do a mid. It will be 0 to 3 and 4 to 7. Okay, that index 2 which I want to go to lies on the left side. So simply go on the left side. Okay, again bifurcated 0,1 and 1,2. 2 lies on the right side. Okay, ignore the left, go on the right side. I will go on the right side. Okay, 2,3. Again, split it 2 and 3. Go on the left side. Go on the left side. Oh, I have reached my leaf node. Now update that leaf node. Update the leaf node to 10. While coming back, recompute your answer. While coming back, I will recompute my answer, which means I will say, okay, whatsoever value was there earlier, no matter what, I have to update it. So I had a 4 plus 10, it will be 14. No matter, okay. Now, no matter what the answer was here, again, 14 plus 3, I have value as 17. Again, I come back, update the answer, 17 plus 7, I will say 24. That is how I can simply get my entire tree by, again, I did a simple point update. I built a single value. So I simply went on to my tree at every node, at every level, updated the root node, sorry, updated the leaf node, and then came back regenerating my tree, or basically saying refreshing my values of the node. As you can simply see, you're going on to one node of a level. Thus, this point update will take a log n time. Let's say the code is exactly same as that of query. If I have reached the leaf node, again, I'll show you the constraints or input. Firstly, you need a v, index of the tree. You need the range for the tree. You need the actual. This is the actual input. You will see, okay, these values are redundant. That's the reason in the code I will show you I have overridden them. But this is the important thing. For the input array A, at this index ID, update with the value val. So you will go on and say that, okay, bro, if you have reached the leaf node, you are good to update it. So update that node, tree node, with this upcoming value or the new value. If it is out of your range, do nothing. There's nothing you can do. That nothing, here it is, identity transformation. You are saying if you don't find anything, do nothing. Nothing as in identity transformation. That is nothing. Okay. If you have partial overlap, for sure, find the mid, do the same recursion on the left and the right with the updated TL and TM and TM plus 1 and TR. And then when this is done, while coming up, find the value of your tree, which means TV will be, I'm doing a range summation, so it will be left node and right node summation, thus building up the tree back. Again, complexity is O of log n. Let's see the code in one go. The entire code you can find on my GitHub, although right now it is not on the website. It is still being built, but soon you will see the entire code with the nodes will be on the website itself, codewitharyan.com. So no worries, you can find from there itself. Now, the code, simply I have taken a class. Again, I have not made a function randomly. I have taken a class just so as to make it clean and reusable. Firstly, if you remembered, you need to make a tree. So for tree, I take a vector. This length is the length which I have taken of the input array. Empty constructor. Okay, I will get the length of the input array. This is the L, length of the input array A, and then I will initialize my length, which is the input, and also I will initialize and say that t dot resize 4 into the length. I showed you 4 into length, 4 into n we take for segment trees, and then my tree T is built of size 4n with the all 0 values. Now the first thing which you could do is simply call this function, exact same build function which we saw. Call this query function. You can do call to query function, exact same function. Call to the update function. Okay. But then we realized all these values are actually redundant for us to pass again and again. So let's do one thing. Let's write a overridden function. So I've written 3 overridden functions, which this function will only require a build of A and will call my main function, which is build function. So it is kind of an overridden function saying, okay, it's A, and then remaining parameters will remain as it is. Same way for query, I'll only pass L, R, remaining parameters it will pass by himself. Same way for update, I will pass only index and the value. Again, this is a point update, so single index is only required, and then the updation. Now comes the actual code, how we will use it. So firstly, let's imagine I have the input array, right? 1 2 1 4 2 3 1 1. Again, I have given the size. You can find the size from here itself, which means n is equals to a dot size. You know that. Build the segment tree. I built this segment tree with this specific size just to initialize my tree array, which is t, of size 4 into 8. 8 is n and 4 is my length, which I have taken. Now, firstly, I just had a simple function call and saying build my segment tree by taking this input array. It will build it. And again, we know the build logic. So far we have applied is a range summation. Okay. Now, simply after building, I just simply queried the actual build. So what happened? After building, the query looked like 1 2 1 4 2 3 1 1. Again, you will see I am actually querying every index. So I'm querying index 0, index up to index n. So I'm asking my segment tree query. I'm not going and asking T0, Ti. This Ti will be wrong. This is a tree. You want to query at the index of the array. So query is simple. This is your object segment tree. Ask the method query, and then it's a point update. So you ask L, R. You are given L, R, but both L and R are same in this case, because it's a point query, which means for an index, what's the value? So I'll simply get the value. Okay. Thus, the input array, which was this, I got the same after querying it. Exactly same. Right. Now, simply, let's say if I ask you again, range query, from range 1 to 5, give me the summation. So from the range, again, 0, 1, 2, 3, 4, 5. From this range to this range, give me the summation. 4 plus 1, 5 plus 2, 7 plus 2, 9 plus 3 is 12. So from range 1 to 5, I got the summation as 12. This is the summation I have got as sum. Update, okay, update at the index 2 with a value of 10. At the index 2, which means at this value, update at with a value of 10. Now, this is a value of 10. 10. Now, again, I am again going in query from 1 to 5. As you can see, again 1 to 5. Simply, it was 1, it updated to 10. So technically, the answer will increase by 9. So 12 plus 9 will be 21. So this is my new answer. Obviously, the new, I have queried the range 1 to 5 summation. So with this, you realized that how did you do a point update and a range query, build a segment tree, a generic normal segment tree by simply using my DFS. Now, don't worry, you can apply the exact same stuff for min, max, or, and anything. And if you want to see the examples and stuff, no worries, keep following, we'll see every example. Now, when the segment tree is done, one thing we missed what? We missed a range update. We did point query, we did range query, we did point update at index 2 with the value of 10, we did not do a range update, for which segment tree is famous for being super simple. Although fenwick tree code might look small for range updates, but it's very complicated to understand and also not much modular. You cannot change it, like it's not versatile. For fenwick tree, I'm saying range updates, right? So let's come on and see that we will now start with lazy propagation. Why the name is given, what it is, no worries, but the entire aim for him is range updates. Okay, so for the range updates, take the exact same array. If I would have asked you, bro, please update the range from 2 to 5. Now don't think of range updates. Think of Aryan has asked you to do a range query on the range 1 to 5. Because that will be exactly same as that of range updates. But Aryan, range query is querying something. Update is updating all the values. Yes, exactly. So if I would have asked you update the range of from 1 to 5 with a value of 10. Technically, if you would have applied the above point update approach, so for this range, for every point inside this range, you would have done the above update query. That update query takes a login time for every point inside the range. So for me, the range length is 5. So for every 5 points, I will apply a login update. So if I use the above approach, which I discussed for a point update, if I use the exact same for the range update also, it will take a O of n login time for one query, considering the range length is n. But I can have many queries. For every query, I'm taking a O of n login time. So for every update, I'm taking a O of n login time. That's not good, right? I should ideally take for range updates or for point update, for range query, for point query, for everything, I should take login time. But for updates, how it will be done? It will be done by simply simulating what a query was doing. So a query was only going, again, if I was doing a query only go to those values which he needs. And we proved it that query will take a login time. So I will only go on to those nodes where query was going. That's the reason I told you, if I would have asked you, do a range query in this range, wherever that range query would have gone to, I will also go on to only those nodes. What I mean by that is that if you remember the above example, simply let's take this range. I'm asking you update this range. So in the very beginning, root vertex v equal to 1, range will be TL and TR. Now for the TL and TR range, you will say, okay, I will start from my tree. Then I will say update this entire range 2 to 7. It's a partial overlap, and you know how to find partial overlap and stuff. We already have seen it. Then in the partial overlap case, you go on to both the children's, left and right. Now on this right range, we'll simply go and see it will be the entire range from 4 to 7. My input query, or I should say my input update, was from 2 to 7. 4 to 7 completely lie inside my query or update range as 2 to 7. So this is a complete overlap. In complete overlap case, and in case of query, you remember, you will not go down. You will return back from here itself. So technically, you are saying, Aryan, if I have given you a task to update a value of 10, in this, for these all nodes, you will not even go on to these nodes. You will return back from here itself by saying, bro, the value which needs to be updated is a value of 10, and you know that you have to update your child. This guy, this blue guy, he is so lazy. He is so lazy. He will not propagate this value 10 to his children. He will say, bro, look, whenever you guys need it, ask from me, I will give you. So whenever, let's say in future, I might go and ask what is the value at the index 4, which means technically I will go on left child, I will go down. So whenever this lazy guy will see, oh, someone is coming to me, now I should give the value to my children. So this is the same lazy maid in the house that she will sleep whole day. Let's say if some person gave some message, or basically let's say XYZ person came and gave, let's say, a few vegetables, so she kept with her the entire day. When the owners came and when the owners asked, I wanted to eat gajar ka halwa, then the maid will go and make it at that point. So imagine she got the ingredients, many ingredients which she need to make. She got the every ingredients. Let's say she got gajar ka halwa, she got many stuff. But then whatsoever was required, only that she made at that point of time. So this lazy guy will store the value of 10 with him. In future, if I'm asking for any query to the down values, or maybe any update also to the down one, which is kind of partial thing, at that point I will go and propagate this value to my child. And same way, as you can see in the left, okay, on the right you saw it's a complete overlap. In the complete overlap case, you store the value with you because you are lazy like me. So I will store the value with me because I'm lazy. But as you can see on the left, it is a partial overlap which will happen because in this range, the range is 0 to 3, and for me the query was, or the update was 2 to 7. So it's a partial overlap. So again, I will go on to my left and right. Again, in this case, it's a complete overlap, which is range 2 to 3, which lies completely inside 2 to 7. Again, in this range, I will store the value with me. I'll store the value 10. This also stores 10. Thus, what happened? You did exactly same as that of a range query. But for the people who are actually not sure, they will see, okay, these values are not at all updated with the value of 10. They are not even seeing that value because this made sure that I'm storing it. If in future someone is querying you, so for sure he will try to go down. If he will go down, while he is going down, I will transfer him value. So why I should spend my energy to transfer that message? No, if someone is coming to you, I will just give him. I'll just give him. Okay, bro, because anyone who comes in will come in via me only, right? So I know if someone's coming to you, I will give him. I will drop him the message. He will give it to you. So that it will help us to simply store those lazy values at these nodes, and thus making us solve the update query in our O of login time. But what's the use of it? The use is simple. Our range update is done. And if in future someone queries it, so on a query I will take a login time, but the benefit is on that query itself, while he would be going down to query something, he can simply propagate that value downwards. That's it. So the effort which update would have taken to himself, he delegated that effort to query or maybe to further some random updates. That is how our lazy propagation works. So how to store it in terms of computer science, how to store it. So I will firstly mark if some node is lazy or not. Then I will also store the unpropagated value. In this case, this node, again, how to know which node is this? Bro, v equal to 1, this is 2 into v, this is 2 into v plus 1, which is 2 into v plus 1. So this node is 2 into v plus 1. So that node, firstly, is a lazy node. So I will take a vector of same size 4n because I have to store for every node if it is lazy or not. If that node is lazy, okay, this node is lazy, and what value it stores as unpropagated value. So it will store a value of 10, saying, bro, I'm lazy, I'm storing an unpropagated value of 10 with me. Now comes the interesting part, that how will you define it? You will simply say, okay, is lazy for that specific node v will be true. That's a lazy node. As same way, unpropagated update for the node v, simply add that value. Aryan, what you did here? Simply, bro, I added the value. But why? Again, that can be a very confusing part for many people. Here, let's say in the very beginning, I set update in this range the value of 10. So you will simply go and store the unpropagated update as a 10. Let's say I ask you update this range with a value of 20. So it's a question for the interviewer, of basically for the problem, that do he want me to assign the update or to add the update? So technically for us, I will add the update, but I could also override the existing update. So if I would say assign or set, which means I'm overriding, so I should override this value to my update. If I'm saying add, which means I am adding the incoming update, so simply add that incoming update, right? So now you're clear with equal to and plus equal to. Plus is adding the update, equal to is assigning or setting the update. I'll show with the problems also in future, but this is something which many people get confused on. Now, when you have assigned, this simply says one thing, bro. Whenever someone is going down, either for querying or for updating anything down, make sure you propagate this value, which is unpropagated value. But I have value of 10. Which means I added a value of 10 in this entire range. Technically, if I ask you, if this node is 1, 2, 3 and 4, so this summation would have been 3, this summation would have been a 7. Now, if this node would have not come in, so this summation would have been a 10. Okay, let's take a worse example. Let's take a 5. So let's say if it is 2, then the summation would have been 8. Now I said, do a range update 10. If I do a range update 10, which means I'm saying, okay, 10 is storing. This 10, okay, lazy, okay, he's lazy. Updated value, unpropagated updated value, which is 10, okay, which means this value needs to be propagated to the children. But this 10, if he will propagate to the children, okay, that's good, but he will also be modified, right? I will have plus 10s on 4 nodes. So technically this will be a plus 20, this will be a plus 40. So it is okay, he will propagate further. When something will go down, he will propagate that further. That is okay, completely fine. But for this value of t of v, it is incorrect right now. Until unless I updated, I know the range length will be 4 to 7, which means tr minus tl plus 1. This is the range length, and this is the update which was I got. Let's say v, or let's say any value. So I got the update. So this update I need to actually add on the existing value. So I'll simply add a 40. Again, this is 4, this is my 10. Adding a 40 in the existing value so as to, okay, make sure this value is correct. All there is below are not correct. Why? Because this is lazy. He will propagate when he will find it useful. So I will need one more thing, which will say update the current lazy node at least. So I'll update the current lazy node. Again, this is updating. If I would have said assign, so you would have simply put a equal to, right? Now I'm saying updating or basically adding. So you'll simply say plus equal to. This is the range, current range. This is the value to be added. And thus I need only these three operations. That is it. And you are good with the lazy propagation. You understand the complexity, you understand the operations. That's it. Only thing required. Now coming on, what I will do, write the code. What changes I need to do? Firstly, I need the unpropagated update vector, which will say for every node of the tree, what is the unpropagated update which they will store. So it will store unpropagated update value. Same way, I will ask for lazy, if that node of the tree is lazy or not. So the way I initialized my t, same way I initialize my is lazy and my unpropagated update value. Cool. Now, again, if you want to add other stuff, everything else is as that of the previous code. Coming on to the change which we will do. Simply, the query will remain as it is. It's just that we know on every query I told you, I need to push down what? Laziness. If you forgot, I told you, if let's say I would have queried for this node, so I would have come query. Now, when I say query, I come on to some lazy node. I should push down his laziness to its children. So this is how I will use my push down function, which means pushing down or assigning the laziness to my children. Let's see the push down code first. So in the push down code, I was standing, again, if you go back, I was standing at the node V, having this range. I need to push it down to my children. For the node V, the children is 2 into V and 2 into V plus 1. So if I am at the V, I should push down the laziness to my children. Firstly, I'm saying push down the laziness to my children. Firstly, am I even lazy? Check. If you are not even lazy, bro, there's no even point to come to push down, right? Yeah. If you're not lazy, simply return back. If you are lazy, firstly, you should make sure that now you are no more lazy because you are pushing down your laziness to your children. So you are no more lazy. So mark yourself lazy as false. Now when we say push down to your children, for sure we should be knowing the exact same parameter for the children also. For if I am coming from the node V, my child will be 2 into V and 2 into V plus 1. And the same way, his range will be TL, TM and TM plus 1, TR. Right? The same way I did here. I will find the mid, TM, that will be simply mid. And then TL to TM and TM plus 1 to TR. Now, when this is done, okay, that was nice. But push down what? Push down the unpropagated value, which was not yet propagated. If you remembered, I was saying at this node, in my unpropagated update value, I have stored a 10. That whenever in future I will do a push down, I will propagate this value. Do the same thing, no? If I will do a push down, I will propagate the value of stored at this node V. Whatsoever at this node V was stored as the unpropagated value, just push it down to your children. And when I say children, I mean both left and right children. Now we'll go on to the push down, like apply also that, okay, you push down, that's okay, but simply pushing down will not make them accept it. You have to make your children accept it. Just simply putting a Coke inside your child's mouth, that will not make him drink it. You have to ask him, bro, please drink it, right? That's the reason you have to now. You have pushed down your responsibility now. It's their responsibility to accept that update to them and mark themselves as lazy and actually update them also. So if you remember, when any update comes to me, I update myself, right? I update myself by this value. I mark myself as lazy. I mark my unpropagated update as the value. Same way, if I'm pushing down the pushing down this responsibility to my children, they also have to follow the same procedure, and that same procedure is made in a different function called as apply. So I will apply at this node this update value, I can say, which means saying firstly, if it is not a leaf node, then mark that node as a lazy node. Aryan, why you have put this condition for leaf node? So basically, bro, if it's a leaf node, then there is no point of marking it as lazy, because you mark lazy saying that if in future I come to you, you want to go down from me, you should, and I will just give it to my children. That's all the use of laziness. For a child who is infant, he has no children, so whom he will give? He will give no one. So if you have reached the leaf node, there is no point of marking it as lazy again, or because you have no child of the leaf node, right? That's the reason. So if it's a leaf node, then ignore it. If it's not a leaf node, then mark it as a lazy. Firstly, update the unpropagated bit value of your child. Again, make sure this is now your child, because it is a 2v and 2v plus 1. So now you are doing this update, again this apply function, you are applying to your child and saying, bro, my child, remember your unpropagated update, you have added a value of val. If I would have said assign it, simply this would have gone. I would have simply assigned it. But here I have added the update val. I'll add it and say, okay, bro, your unpropagated update value will be now incremented by a val. But no matter if it's a leaf node or a non-leaf node, one thing for sure will be required, which means incorporating the update to at least me. This unpropagated update says, just simply say that propagate to the child, right? That's what this says. This says, at least I should be satisfied. So what I will do, basically this child will satisfy himself, his greed, his need, not in that way, not in the Mumbai Pune case. So what he will do, the child will satisfy his greed by updating himself, basically updating his range, or basically his node value with the new update, same as what we did previously. So this is how you push down your responsibility or your laziness to your child, and then how your child or any node will apply that laziness to himself. Cool. Let's come back to the query from where we left. So here I said, okay, if I have a partial overlap, which means I'm kind of going down. If I'm going down from a lazy node, I should propagate my, or I should push down my laziness to my child. I'll push down laziness to my child. Simply, no matter if you push down or not, it asks us to query. Go back to your query. Your query code exactly same as it is. Update. Simply, again, as it is. Simply saying, if it's a complete overlap, apply that laziness right now. You are updating in the range L to R, right? If it's a complete overlap, I showed you. If you go back, if it's a complete overlap, apply the laziness right now. Apply the laziness. So I'll apply the laziness. I'll apply the laziness right now. Again, the apply function will apply the laziness right now on this node V, right? And then simply return from here itself. Don't go down. In the no overlap case, simply return with identity transformation. Here it is empty. Now, in case of partial overlap, you have to go down. In case of partial overlap, you have to go down. Now, while going down, make sure you push down if you have a laziness at V. So, same way as we did in query also. If you're going down, simply push down. So, if I'm going down, I will push down. And we have seen a push down code also. And thus, exact same code as it is. And voila, just a 5-6 line change, a few addition of 2 vectors, and we have written our code for segment trees with lazy propagation. Let's see the code in one go. Again, the only thing which is here is the apply function, and again our pushDown function, which is used. So here I've just written that same thing I was telling you, that it is assigning the update, it is adding the update, which significantly have a difference by saying that if I assign an update, as you can see, exact same main code I've written. Here I have the input array as 1 2 1 4 2 3 1 1. I firstly printed that array, as you can see, this array printed. Then I did a simple range query, same as last time. I did a update, point update, same as last time. I again did a query. Okay, no worries. Here this is simply updated to a value of 10. Again, this is a updated to a value. And you remembered, I was doing a addition. So update, it is updating. If I have value 1, it is update. Add a value, adding a value of 10. So I did update, I add a value of 10. Value of 10 is added on the existing one. Right. Again, you can see this is the output which you have got. If I ask you update the range 2 to 7 with the value of 10. So 2 to 7 range, add a 10. Okay. In all of them, I will add 10 and then add a value of 20. So I'm on top of 10. I'm adding a 20 again. So ultimately I'm adding a 30. So I added 30 in this range, and thus I got this is the new entire range. I added 30 added on the existing values, and thus I have got, thus it is just showcase that this is the addition in the update. What if I ask you assign the update, override the update? So in this case, when I say override, so at this index 2, I said assign the value of 10. So 1, it became a 10. It got assigned. So it is assigning the update. And same way, if I did ask you, okay, update with the value of 10 in this entire range, then I modified it and I said 20. So now the new assignment will be a 20. So you saw I did a 20 assignment to the entire range here. That is the difference between addition and assignment. People get a lot confused in this. That's the reason I tried to clarify this. Let's see the code again in one go. Again, the entire code you can see on my GitHub repo. You can star mark it. I will again, this you will see the Sublime snippet. If you don't know, I use Sublime as my CP editor. So the usefulness of that is you just need to write this code, let's say segment tree underscore lazy, and you will get the entire code. If you want to copy this, you will simply have a comment on the top, and ultimately in the end, just copy that portion and you will have it. For the folks who use Sublime as their CP editor, they can just import that file and use it in their Sublime library. Now the code in one go. Firstly, we initialized and got those variables or those arrays. Then we had our apply and the pushDown function, which we discussed. Again, you can read these comments. It is for your in future, if you let's say come back to the code, you can just refer those comments also. This is the build function, exactly same. This is the query function having just the only pushDown change. This is the update function having the apply and the pushDown, and then the same overridden function which we had previously, and the exact same main code which we saw just above when we were discussing our range update or addition as an addition as an update or assignment as an update. And thus we have done our lazy propagation of segment trees or segment tree with lazy propagation. And the same thing will work for min, max, XOR, OR, and everything. We will see everything also. Now let's come on. Okay, we have seen the segment tree. We have just did a tweak and received a lazy propagation. Now we will do another small tweak to generalize that segment tree code. If you go and take a look back, your look back will just make you wonder that the only thing you were needing to change was kind of these values. But Aryan, to make it generic, you are taking you're taking this array t as int. it was int for you, right? Int. But I can take my node, because see, this int is a node of a tree. That can be a pair also, that can be a vector also. So now we will try to make this entire stuff as generic as possible. But the prime operations, imagine that you have a node, imagine you have a tree. Now give me what are the prime operations you will require for it. I will ask you, the prime operations will be, firstly, you can merge two nodes. Why is this the prime operation? The prime operation for you is, if you do a query or if you build a tree, while coming up, you should apply some operation to merge your two children, right? So my one prime operation which I use both in building, query and update will be merging my two leaf nodes to receive myself. So let's say I have a left child, I have a right child. I will merge them by some logic and will get a V. Now that some logic will be my merge function. So in this case, so far we had been getting a left, we had been getting a right, and then adding that up and thus getting us a V. So imagine you have a left node, imagine you have a right node, simply add them up and you will get a V, right? Okay. Apart from it, what is something else you must be knowing right now, which is update. Now, for update, there were two major stuff. If you forgot, for update, there were two major stuff. Where is the code gone? Yeah. Firstly is combining the update. First, it is combining the update. As you can see, here the update is combining, which means adding in the existing update. The next is applying the update on the node, right? I'll use the exact same stuff. So I know I have to combine the update, I have to apply the update. So if let's say I had update 1 coming in, okay, I have that update. Let's say I have update 2 coming in. I know my combination logic is saying add the updates coming in. So I will add the update. If my combination logic says override or basically set the update, so I will simply would have set the update to update 2. This is my combining logic. Now, after combining, I should have a applying logic. Now, if you had got this updated value whatsoever, apply that to the current node of the tree. We remember T is the tree node for us. So I will apply that update on the current node. That is the applying logic. So these three are the only logic which we have to change. That's it. That's it. That's so beautiful, right? So we realized, we figured out these are the only three logic which we need to change. So we will separate them out from the entire code and then we will build the generic code. Now, I have been speaking enormous times about the identity element and identity transformation. Now they will be used because now things are becoming generic. If I will repeat once again, identity element says do apply some operation on it, it will remain same. So if I do a x plus 0, I will get a x. Identity transformation on x says, let's say x. So if you have to combine something on x, add as like have a 0 on combination, you will get again get a x. So adding, let's say transformation which you are doing, so it's an identity transformation which you are doing here. Cool. Let's see what we need. We will take a node class. Again, I've taken node class. The use case why I've taken these classes is they can be generic, as in like you can use them, you can make objects of them. But that's not required because C++ is very awesome. You will see how. Firstly, I will need a node. That node will store the node details. If you know this is a tree, for me this is a one node. So far this one node only contained one value which was v, and that is int. Same way I have done here also. Again, you might see I have written public in overall. I usually give public. I know it's not a good oops practice, but no worries. It's not a oops video. It's not a design video. So please ignore it. I have made public. I might have taken struct also. I know it's completely fine, but yeah, I love classes. I don't know why. So I took that one. This indicates for this node, I have these values v. It can be variable also. I could have had a vector of int also inside that one node, which means every node is containing a vector of int, vector of int, vector of int. That's the beauty of it. Okay, great. But so far, let's say I have a 1. I'm just replicating this generic function exactly same as that of the above code of lazy propagation. Although we will discuss the more variations, I will have minimum, frequency, all that stuff. No worries. But this is what we have taken. Now, this, you will see, okay, it's 0. What it is, you will see. But so far, we have seen that we have an empty constructor, which will initialize that default value with this identity element, you can say. Now, this is a constructor which you wanted. If you want to initialize with a value of val, so get this value of val initialized. Then it's your merge function, which will have incoming node, left node, incoming node, right node. You will merge these nodes and will get the new node v. That's a merge logic. So anytime you need to do a change, you need to change this identity element, right? You need a may, or again, that's optional. You could be wanting to change your constructor when you initialize that val, and highly likely you will be changing this merged function. So in the code, you will be only needing to change these 3 values. Again, for this node, okay, that node part covers our merge logic roughly. What about the update? Okay, for that I will have update as a class, in which I will have identity transformation as 0 in the very beginning. Again, same empty constructor, same, I initialize with the empty value, let's say value of a v. If I want, I had a combine and apply function, if you remembered. Combine says you will get this, you will get some other update, you will get, and then you will apply this other update on your existing value or existing update whatsoever you had taken. This is unpropagated update, if you remembered. So this is same way same way saying for the other. Again, remember, this other is the newest update which I'm applying right now. So I'll apply this other update on my current v, right? Same way, apply this current update. Basically, apply this current unpropagated update value to your current node v. So I had a node which is our above node class. I will apply that inside and will get the answer. Okay, update done, node done. Everything remain exactly generic. So in this also we realized we need to change either our identity transformation, or we should change our update constructor, or and our combine logic and our apply function. So these are the only 7 changes which you would be needing to do in primarily most of the cases. Now comes the part where this tree is now generic, or the segment is not generic. For C++ folks, to make things as a generic, we have a template saying I will have a node and update. Again, these have no link with the above node and update. No worries. These are any names you can give. This ultimately indicates that whenever this segment tree is called, so I will call this segment tree, then I have to pass in 2. I have to pass in 2 objects. Whatever I pass in, that will be considered as a node. Whatever I will pass in, that will be considered as an update. So here you will see I will use many stuff. I'll use update, I'll use update dot apply. So if while initializing your segment tree, I'll say okay, seg tree, oh I should say st, let's say I should say st. While initializing that segment tree, if you pass something absurd which do not have a apply function or a merge or a where's it gone, or a merge function, if they don't have it, for sure it will give an error. So it is simply saying that whatever you are putting here, this should have a v, this should have a simple merge function. This update says it should have a v, it should have a simple node, like, or I can say apply function or combine function. Right, now coming on back, same segment tree code. Earlier I had this, no worries, I just added identity element and identity transformation. If you know, for node I told you I need an identity element, update I need identity transformation, so I just simply have that. In the very beginning I initialized to a empty identity element. If it is empty constructor, it will simply go and assign with a value of 0. Thus I told you that this indicates our identity element. Same way for identity transformation, update constructor called, it will go up and it will assign my identity transformation as a 0 again. Now apply function, if you remember apply function, same, exactly same. Now we'll just use our object which we have made. The unpropagated update which we had, because if you remember this is the vector which we had, this unpropagated update, it's now the vector of update, which is this update, and this update is actually we will pass in as the update class which we have. Now this name can be anything, this can be update 2, node 2. I just have to make sure I should pass in here as node 2, here as update 2, while initializing my segment tree. Right, now in my unpropagated again, in my unpropagated update for this node, earlier I was simply combining manually by writing a plus is equal to, right, if you remember. But here I will ask my combine function to combine it for me. I will pass in again this update. You will see the flow later on, but I'm just focusing primarily right now on apply and push down. Then I will show you how this update is passed and all that stuff. But you will simply pass in this update, you will pass in the range, and you will simply go and tell, bro, simply combine this update on your existing update. So you will go and ask your combine function. The combine function will say, bro, this is the existing or the newer, it is the newer update which is coming in. I should apply this newer update on myself. This is a newer update. So if I come back, I'm simply saying this is the newer update you should apply. Yeah, it is a newer update which I should apply on this node v. Now after combining the newer update with the existing update, I have got the value. Simply now say, okay bro, whatsoever update you have got, apply that update on the current node, which is EV. I will firstly get this node, and then for this node I will apply, as you can see, this is the apply function, apply logic. We will simply apply this existing v whatsoever I had, I simply apply it on my current node v, and I'll get my answer. So I simply applied my current on my current node, I simply applied that, and I am good to go. Now when this application is done, your main apply, again apply, you might get confused, but this is updates apply, this is your segment tree apply. This segment tree apply is used in your push down, if you remembered. How? Simply push down is same. If it is not lazy, return. If it is lazy, then firstly make it as a false, find the mid, apply on left and right, apply on left, apply on right. Now apply on left what? Apply this unpropagated value. Same way, again, when you pass in a value to a class, it automatically goes to your constructor. That much C++ you should know. Now, when this application is done, make sure to put your default value of unpropagated update to a, if you remember, you were earlier putting as a 0, but now you know you will put as a identity transformation, which you have already initialized above. Cool. The same thing as a change will be done in your build, but you can build this vector out of any array. Earlier the array was the integer vector, but now it can be anything. So again, I made a template, type will be t, then made sure that same code, exactly same code of build, is just that while merging the two nodes, call your merge function on this node v. So I will say this is my node. This again, this tv is a node. If you go up, you will see this vector t is of type node, and this node we have initialized with our node 2, and this node 2 is our this node 2. Cool. So if I come on back, I will say just ask your merge function. I will give him 2 child nodes. You just have to merge it. So he will come on to your merge function. He has got 2 child nodes, and again child nodes. By whatsoever logic I want, I can just merge those 2 child nodes and I'm good to go. Okay. When this build is done, let's come on to query. Query exactly same. If it is outside my query, return the identity element. Striking, why? Because I want to return something which should not impact my query, and that is my identity element. Now if it is in bounds, completely in bounds, it means completely overlap, simply return the node value. Now for partial overlap, make sure to push down first, the code we have already seen, exact same code, but while coming up, make sure to not do a addition manually, but ask your merge function to merge your left node and the right node. And this is the left answer, and the right answer is it's the nodes for us. They will return me node. You can see I returned a node, not integer now. Cool. And ultimately return the node, not the integer. Same I will do for range updates also. Again, same for range updates. If it is a completely overlap, simply apply. This apply will go on to your apply function, which will firstly combine my update and then apply that update. So I simply called my apply. The only thing which you will see is I have a update called. If you remember earlier, when you were calling your range updates, you would pass in a value. So from my main function, if I show you, I would pass in a value of 10. This 10 value will be passed to my this function lr and update value 10. Now a 10 value comes on to a class. It will be initialized by a constructor which we have defined, and will initialize the value v of update class with the value of 10. And thus this update is now basically saying I have an object having a value of having a attribute or a you can say variable having value of 10, and thus it is being propagated to the update function. Here everything is constant and passed by address, so nothing is changing here at runtime. Whatever I'm passing in, I'm not bringing any copy at all. I'm passing in the same constant objects. Constant is just that it is not modified, and address is to pass in by address and not by value. Now I will simply have applied that update on my current index v. Now this application apply is done. Again, this apply is the segment tree apply. and make sure the segment tree apply calls in the combine function of update and the apply function of update. Now, again, if you go and look back very very deeply, you'll see it's a update. If I will call for this update in my value, it is being passed as a constant. So if I am for a constant, I am calling an apply. It should make sure that it is also constant. That's how small this like things in C++ are. Now coming on back, we know that we will simply apply the update when this apply is done. Again, if it is no overlap, simply return. That's no point. If it's partial overlap, push down. While coming up, take help of your merge function. Exactly same as that of your query you have done. Now overridden functions exactly same. It's just that now your build will need a type name as t, because you need to build in with the arbitrary vector. It can be a string also. Now query and range updates same as what we have seen previously. It's just that it needs a update, which I can simply pass in a value also and will update. It's a simple constructor, right? Yeah. Now let's see the code, how we will code it. Vector same as it is. Just that while initializing my segment tree, I need to pass in node and an update. Now the beauty is that if you have one segment tree which needs, let's say, range merge operation and range, or basically addition, if it asks you give me a summation of the range, and if it asks you I will give you a update and you have to add that update in your range. Okay, for that I will use this node to an update to. If let's say on the same problem I ask you that, bro, I have to make one more segment tree which will do a or in the query and XOR while update, then will you make the new segment tree? No, you will just make another node 3 and update 3 as the classes. And then when you have these two classes having all these required attributes which you want, you will just make another segment tree saying I will make a segment tree having a node 3 and update 3. I will name it as segment tree 2, and that is how I can use the segment tree 2 in my answer, in my problem. That's how I can use 2, 3, 4, 5, even n number of segment trees in my same problem. I just have to make new node and update classes. That's it. Now coming on back, I'll build my A. Everything will make sense because it is integer right now. Even if it would have been a string, still this build would have worked because it is generic on T type. Cool. Now exactly same code as we had seen previously, exactly same code. Let's see that how the code changed, or how the answer will change considering what we will change. So again, as I showed you, I will only change my node class and update class. Everything 95% of time will remain static. I'm not saying that your main segment tree code will not be changing. It can change, but very less. So as I showed you, let's say I ask you do a range addition, but the update will also be added. So I am doing a range addition. I know when I will merge my two nodes, I need to add them up. L dot like left dot v, again if the value is v. If you remembered, in my node I have put the value as v. So the value stored in the node is integer value which is v. So it will be left dot v and right dot v. So if I'm asking you do a range query, or basically do a range summation, so you will simply merge. While merging, you will do a range summation. That's what you wanted. Okay. For update, I am asking you do a update. You have to add in a value v. You have to add in, let's say, any update value, let's say val, in your range. It is an addition of update. So you will see I have done an addition of this. Again, this other bit is the new update which is coming in, and thus I have applied that update also here in this node. Cool. Thus you will simply see that I did a apply. So apply 1 added 10 became 11. Then I added a 10 and then a 30 and then a 20. It became a plus 30 in all of these nodes. Thus, you can simply see this is the only change which I need to do. If I would have asked you, do a set of update. So now I have set my update. I'll do exact same stuff. Now it has set to 10. It has set to all 20s. That is the exact same problem which we have seen so far. Now, we saw everything for the generic piece of code also. Now, if you want to look at the entire code at one glance, it is exactly the same code which I showed you, right? But there's one a bit extras which you will not be hearing, but still for extras, I will just tell you that there is called as a descent in segment tree, which is same way saying if we want to do a binary search on segment tree, then we use a descent. Again, we'll not go into it. If you want to study it, you can just do CP algorithms and you can just check out there because it's not that not that much use, but still internally if you go and look, you can still implement it. We also have a merge sort tree. It's just simply can be done easily via our segment tree which we have built above. It simply says that you have few nodes. While building the tree, again, the nodes are not just one integer, it's a vector of integer. And I know our generic code can handle a node. Inside the node, I can also have a vector of integer also. So here I have vector of integer. It's just that while building up the array, I am actually sorting them up. It is being sorted while the array is being built. As you can see, it is a merge sort tree, which is the same method of merge sort. The use case of the problem which it brings in that you have given an input array, ARR, as you can see, input array 152 fun input array. You're also given the queries of type L, R and an extra attribute or extra variable called as K. Your task is to find the number of elements in any range L to R such that those elements are strictly more than or strictly less than your K. Again, it's a simple range query. If it's a complete overlap, apply a simple binary search on this input vector. Binary search by simply saying upper bound and lower bound. Apply binary search and get the number and simply return that number. If it's a partial overlap, simply go left and right. That's how simple is it. Simple it is that in a partial overlap, go down for sure. In complete overlap, apply a binary search on that vector which you have stored in your node and then try for, again, binary search you can implement yourself also, or you can simply do a lower bound upper bound also. And then if it's no overlap, then simply ignore. Now you are completely done with your segment trees. Let's have some. I will discuss 9 practice problems using the exact same code which we have seen, and then one just last showing, okay, they can be multiple possibilities, and then ultimately I will give you some, or you will see 30-40 practice problems for you to do also. Now, again, the code you can find here for this specific practice problem. For the remaining ones, you can easily find on my GitHub repo. The code is generic piece of code. It is that only used. Cool. Now, for this problem, how it is special? It will cover that a node can be anything. Here I asked you, you have to find the minimum in the segment, minimum in the range, and also find the frequency of that minimum whatsoever is there in that range. So, you have to maintain two things. Firstly, the minimum value and also maintain the frequency of that minimum value. Just to be more precise, the operation says that at an index I will give you a value v. You have to set, see, whenever you read this, you should ring your bell. How you have to optimize your, or how you have to write your segment tree code, right? You have to set the elements with the index I to this value v. Cool. Again, this can be a range also. I will discuss both of them. Although in this question I have given you, let's say you are modifying the index I with the value v, but I will show you how you can modify the entire range, how you can update, how you can set the entire range with the value v. I'll show you both of them. The next operation is in the range L, R. I will ask you to query, and the query you should return me the minimum in that range L, R, and also the value, or basically the frequency, the count of number of elements who is that minimum. So we realized that how should our node will look like. Our node will look like by saying, in my node I will have two variables now. One variable will be minimum, or basically integer. Again, depending upon the constraints of the problem, you should define, again, as you can see, the v for me, the update is 0 to 29. Depending upon these constraints, you should decide your identity element, or you can say the minimum element for you. So I told, for me, in my node I need to contain the actual element, which means the minimum value and the count of that minimum value. Both are integer, but I need two values now. If you would have written the code by yourself, then you would have to modify your entire segment tree by taking a pair of int comment. But now you have a simple class. Take just two variables, or you can take a pair also. It's totally up to you. But you don't have to touch the entire code. Just touch the small piece of code and you're good to go. And same way I will have on the right as minimum and count. When I will merge it, I will again get a minimum and the count. But how the merging will look like? Merging will look like, okay, minimum will be minimum of the left child and the right child will be a minimum. So my minimum will be this, minimum will be minimum of my left, which is L dot m minimum, and right dot minimum. Cool. Now, what about the frequency or the count? Simply the count. If this minimum, again, let's say if this minimum was a 2, minimum was a 2, count is 3, minimum is, let's say, 3, count is 1. So I will simply say, if this minimum is same, okay, copy the count 3. If, let's say, if it would have been 4, simply if this minimum 3, copy the count 1, simply copy the count. So if my minimum is equal to left minimum, just add that left count in my count. If, again, this is not else if, this is if it is equal to my minimum, again, if my right minimum is equal to my minimum, then copy my right count. Why it is used, Aryan? It is used because what if both are 3? The minimum is 3, but the count is 3 plus 1, 4. That's the reason I have added if condition. Okay, my merge function done, sorted. Simply combine function. You have said set the value. So the update, the other update which will be coming in, I just have to set. As you can see, this is equal, which is set. I have to just simply set that other update to my v, and same way just apply that update. So whatsoever v I have, simply apply that update. Simply apply that update. How? Simply by saying that I will have my node. I should firstly set the value to v. It is a setting value which we are doing. It is a value which we are setting. So in the node, I should set the value as v. Then I should make my count, my new count will be tr minus tl plus 1. Because this I am setting for this entire range. If this range had the count of 4, which means I had 4 elements having this minimum value, let's say 1 is the minimum, is the minimum value, then I am setting it to, I am saying, okay, now the minimum, now the value is minimum is 4, sorry, 8. The value is 8, still the frequency will still remain 4, right? That's the reason I am doing a tr minus tl plus 1. Cool. Thus, this is the only thing which you need. So let's see the code. That's how soon we reach the code. The code simply says that firstly, we will initialize with an identity element. For me, v, or this is the minimum value, it needs to be minimized. So I initialize with the maximum value. That is that it does not affect my answer. Same way for count, its identity element is 0 because a count of 0 will not affect my answer. Then the constructor, when you received a value, okay, update your value with a value, and you have got one value, so make your count as 1. Okay, your merge function, you have left and right, Write the same code as it is. Same code. Update function. Now your identity transformation 0 because simply it's a set. You can simply have a by default of a set as 0 in the beginning. Then you can just simply keep on setting it. As you set some value, just simply update that. Okay, so constructor will have the value itself. The combine is setting the value, so it is equal to. The apply also is setting the value, so it is equal to on both sides. Cool. And that is how it will work both for your point query, sorry, for your point update or point set also, and a range set also. This is the only change which you required to solve your answer. Cool. Again, remaining code remain as it is. Let's see how the main function will look like. Firstly, exact same I just printed the exact same array. Then I said that, bro, do a range query from 1 to 5. So 0, 1, 2, 3, 4, 5. 5. From 1 to 5 in this range, what is the minimum? Minimum is 1. What's the frequency? Frequency is 1. So minimum is 1, frequency is 1. Okay, done. Then update the, again, it's a point update, but range update will work also because it's a simple lazy propagation for us. So 2 at 2, which means at the index 2, update with a value of 10. Again, this is a setting of a value, so it actually did a set. Now this is my new array which is there. Now again I'm asking for a query. Again, query from a range 1 to 5. What is the new minimum value and the count? Now this is the same range from 1 to 5, but now in this case, as it is updated the value 10, the new minimum is 2 and the count is 2. New minimum is 2, count is 2. Okay. Then again, do a range update 2 to 2 as 1, which means index 2 to index 2, I updated that to a value 1. Index 3 to index 4 again as 1. Index 3 to index 4 again as 1. I did the update. Now in the last query I asked, bro, from 2 to 5 give me the minimum and the count. From 2 to 5, 2, 3, 4, 5, 2 to 5 give me the minimum and the count. Minimum is 1 and count, as you can see, is 3. That is how I have simply used. Again, you saw that I only changed these two nodes and got my answer. Cool. Now let's see some other code, other problem. We had already been walking through the range sum query and range updates. So this is already covered while you are seeing. Other could have been a range minimum query, which is again the little brother of my this problem. It's just simply remove the count altogether. You don't need count at all. That's how you can simply solve it, which is range minimum queries. What about, I ask you, you have to add to this range L comma R. Again, I would have written the L and R, but it is same as that of what we saw in problem 1. The constraints are all same as that of problem 1. Cool. Now add to the range L comma R, and then another is find the value at the index I. Okay, I'm saying adding to the range L comma R. What's simply adding? Adding is simply updating. Updation is actually addition now. So this is now addition. The operation is now addition, and then find the value. Okay, it's simply a query. Now for a simple query, you might feel like, Aryan, there is no merge operation which he is asking me to do. Yeah, correct. So you can just put a by default merge operation, anything whatsoever you want. Yeah, just put a plus. If you want, you can do anything because he's only, okay, my battery is dead. Because we can simply use any merge operation and that will work for us because we are just querying for a simple point. Although if we would have asked for a range query, then we could have just written, okay, if they want the summation, just do the summation. If they want the maximum, do the maximum, all that stuff. Cool. That is, we are done with the problem number 4. Problem number 5. It simply says set the value V in the range L to R by the operation AI is actually maximum of AI or V. It is not a setting the value directly to V. It is setting the value to whatsoever is the existing value higher. Okay, that will remain as it is. If the incoming value v is higher, it will become v. So that's how I'm setting a value v based on this condition. That's a different thing, right? Yeah. And for the query, you have to find the maximum value in this range L comma R. Now, if I check for the update, it's simply assigning the update. So I'll simply assign the maximum of existing value and the newer update coming in. To apply the latest update, I will simply apply the latest update by simply maximizing the existing value of the node and the new value of update. Now, for query, you now you want maximum value of this range L comma R. Simply, you can take that v as 0 considering your minimum value is 0 itself. If not, then take as minus infinity or minimum value. Cool. You have to just take the maximum out of both of them, and that's it. All set. Cool. Now for problem 6, it says that you have a range. You have to assign the update on this range L comma R with this value v. Straightforward assignment. So I'll simply assign this update in this range, and I have to do a range summation. So I'll do a range summation. That's it. Next problem. Add v to this segment, but find the minimum of this segment. Okay. I will add v. Again, this is addition of v in the segment, addition of v in the node, and finding the minimum. So finding the minimum. So merging is actually minimum. Okay. Next problem. Multiply all the elements in the range L comma R with this number or the value v. And this is the update operation. The query operation is find the sum of the elements in the range L comma R. Cool. So multiply, which means how we'll combine it? We will have the v. We'll multiply our latest incoming update with a v. Make sure that depending upon what the problem is saying, it can overflow depending on what the constraints are. So for me right now, let's say I'm saying if it overflows, have a modulo with 9 plus 7. So I will have existing v, I'll multiply with the new incoming update and I'll do a modulo. Same way, I'll apply that on the node with the existing update. I will simply, in the existing node value, I'll simply have this v multiplied and do a mod again. For my summation of elements, it's a simple summation of elements. That's it. Again, mod I have done at every step you will see. Else, this is my update. This is my node. Cool. Now, problem number 9. It simply says apply the operation ai equal to ai or v. It is a bitwise or, if you don't know, to all the elements in the range L comma R, and then find the bitwise AND of all the elements in the range L comma R. So the query is asking for a AND. So I'll do a AND in the query, while the update is asking me to do a OR operation on the existing value. On the existing value, I'll do OR operation, and same I will do for my node, and thus get my update done. Now, this same multiple such combinations can be there. Assign the update, then do a min query, maybe do a set of your min value and do a range addition. So now it can keep on going. Now, for you, these are the practice problems which you can, again, link will be in the description below, or you can just go and visit Code with Aryan. In that also you will have the entire documents, again, probably in a month, because that is still in a building phase. I hope you guys liked it. If yes, then please do smash the like button, and please do share with your friends so that the reach grows and it can reach to more people and more people can take advantage of it. And yeah, thank you so much for watching. Goodbye, take care, bye bye. Please like it if you liked it. If not, then okay, you can like simply dislike it. But if it was helpful, please like it, and please do comment and tell me how to learn from it. Bye bye, take care.